All right.
Oh, did you actually implement this?
Oh
yes.
Yeah, this is a
When they use
full-blown
it.
tool. This is gonna be fun.
Yeah.
All right, so we are started.
In production.
Welcome to Chalk Talk, whatever the hell we are. No, 397. We're almost up to 400. And this is Rishabh. Say hi to Rishabh. And well, actually, we're watching that screen over there. Rishabh's been at Digital Main for like almost 2 years now, right?
Yeah, 2.5.
2.5. He's going to talk about this cool paper. So take it away, Rishabh.
Cool. All right. So what I wanted to stress upon was this is not just one paper. What we set out to do was to somehow find a way to do shape interpolation between some random shapes. And it just turned out that this linear rotation invariant framework and the linear rotation invariant coordinates candidate for doing that.
Cool.
So it's actually a mix of a whole lot of different papers because a lot of people do touch upon this idea and this mesh representation in specific. So I guess I might just pick different parts from different papers.
Cool.
But yeah, that's why what I want to say is it's shape interpolation using the linear rotation invariant coordinates and not the paper. So the idea is, first of all, we want to do this shape interpolation between very organic poses of some sort of a character or maybe just generic models of some sort. And we want to do that while it looks physically plausible.
We're going to switch to the computer. Hold on before we. The computer, and I'm gonna just do this.
So starting from a sleeping panther to this kind of a pose, with linear interpolation, you have vertices going through themselves and just isn't the physically plausible behavior that you really want. So the other example is where you want some sort of a behavior like the twisting bar. So on the left is the linear interpolation through each other, and on the right is what you really want to see ideally as the in-betweens going from the neutral bar to a twisty bar. Right.
Having the start mesh and the end mesh,
Correct.
And it's figuring out everything in between. Okay, cool.
Right. And ideally, we'd want to handle these kind of extreme rotations as well. We would want to preserve some sort of as rigid as possible energy or some sort of a volume preserve. And be easy as well. So you don't want to keep tweaking parameters around to try and get this to work. So the thing that you turn to immediately is that there are so many mesh deformers that have come about in the last decade or so. So if you can break that mesh deformer technique apart and give you the in-betweens, would that work out? Fortunately, with the mesh deformation schemes that got very popular, most of them depended Laplacian energy or the Laplace operator, which kind of encodes the curvature changes on a surface, on a local surface, but the Laplacian coordinates or anything that comes out of that Laplace operator is baked into your Euclidean space, which is coordinates. So in a scene or in word space, it would all be on this x, y, and z values. So the problem that happens here is when you have two different meshes with two different Laplacian coordinates or differential representations, finding out how to interpolate between those two different looking rotations or two different looking local patches on the surface. Quite an involved problem, and there's no easy solution to it. So you might have to get into nonlinear solves. So the results that we get with a good shape interpolation technique is achievable using the Laplacian coordinates as well. But what happens is you don't get as good a performance as you want. So what we turn to is idea of some rotation invariance in your coordinates. Basically, what I was on every single surface which is embedded in R3 or the world space, for a local patch, there is a certain curvature defined for it. This curvature is usually in literature called as first and second fundamental forms. The first fundamental form kind of encodes how a surface is defined on a tangential plane, and the second fundamental form defines how it's related with its normal. But the main point here is that if I have a certain one ring on the mesh, and if I have the drawing really sucks. Maybe it's not very clear with this. But what I do have is a video of some.
Let's go to the video.
It's Jupiter.
So with the change in shape, you kind of see the change in curvature values as well. And all of these values are scalar values defined on the mesh. What we ideally want, and the key point here is that even if I rotate and translate this object, all of these curvature values are never going to change up to a rotation and translation. So what tends to happen is all the information that I really need to get this mesh representation, to get this kind of a surface, are those curvature values. So if I can go from the starting pose where the curvature map looks like this to a curvature map which looks like this, and fill in or interpolate through these curvature values, I can generate a mesh which is an interpolated surface between those two extreme poses. Right. So what we want to ideally find is somehow to somehow represent these curvature values in a representation which we can then use more efficiently and realm of things that we already know as and the kind of tools that we already have developed. So one of the ideas that came about to use these curvature values was something called pyramid coordinates, which uses the angles between the triangles that form the one ring on every single local patch. So it's encoding all of these angles between the adjacent sides, and it's also encoding the edge lengths. For a deformed version of this one ring, all I'm going to really do is just interpolate between these angles and these edge lengths. And if I do it properly enough, whatever in between I get, going from this pose to this pose, I'll get something plausible and something that looks physically correct.
So if I have the center vertex and the angles, I can recreate the polygonal mesh in 3D?
Yes. So the way it's going to happen is you go down this route where you encode this mesh representation, which right now is in the form of XYZ, XYZ for every single point. To break it down to some angles and some edge lengths. You have the deformation happen over here by some sort of an interpolation. And you get new values of angle and edges, and then you can go back to your Cartesian coordinate space or the Euclidean space to get the mesh back. And this is the kind of workflow that we are going to follow as well with linear rotation invariant coordinates.
Hold on. Yes, Frederick?
Can you fix the focus? We
Nope.
cannot read it.
Yeah, hold on. Let me check. Nope. That's what I want. Nope. Wow, that sucks. You guys should have spoken up. There you go. How's that? That's better.
Thank you.
Wow.
Yes. Okay, that was bad.
Cool.
Okay, over to you.
Perfect.
So this is what pyramid coordinates did, and a paper came out in 2003 or 2004, which gave a pretty good technique for morphing from one shape to the other. To be a nonlinear one, and it just doesn't scale all that well. And the way to actually have a much faster technique is to somehow find a linear way to represent all of these quantities, which are rotation invariant, and then come up with smart linear systems where we can solve them really quickly. So that's what the linear rotation invariant coordinate paper proposes. So what it's actually doing is basically trying to encode this first and second fundamental form, which I mentioned that this one somehow encodes the tangential information.
You're going to have to explain that.
Yeah.
You don't get away with somehow.
I like this.
Yeah, totally.
It's his first.
Yeah,
He's
it's his first one.
Gotta get hazed a little
But
bit.
go back to your drawing and say how the tangential data gets, because it's important, right?
Not really, no.
well,
But do it.
You got to do it.
So, all right. Only I could draw in 3D. Right.
Okay.
So what's going to happen is single 3D surface. We can parameterize space, which is made up of just two axes or two bases, u and v, and then flatten a mesh out from its 3D state. And the curvature change that one sees, or that we can compute over a small patch in two directions, in these parametric directions, is what would define the tangential change in the curvature over that local region. And with that, what we kind of get to know is how the mesh's curvature is changing, and those are just some differential quantities stating that the mesh is concave or convex in that region. And but that information isn't enough because it doesn't capture how much concavity or how much convexity does the surface have, and that the null captures. So the more concave your convex your surface is, the normal is going to change really fast. So your second fundamental form kind of has higher differential values across the surface. And then in a way, tangential information gives you the differential changes in two axes in this 3D space, and the normals are giving you the change in the third axis, third dimensions direction. Kind of not a really good explanation, but
well, actually,
yeah.
I mean, it kind of was, right? You're coming up with a different way of encoding the mesh. Instead of X, Y, Z points and edges,
right.
you're now saying the tangential plane. So you look at the normals of all the triangles that are around that point to figure out the tangent that's going through that point. And you basically project those edges onto that tangent and see how they're changing across the, because there's an infinite number of planes and is going to control the amount of change. So you need to choose a plane, right?
Right, and that plane is defined by the norm.
Yeah, and then the next, right. So it's a different way of encoding the mesh. And once you go into tangential and normal, once you go into those two forms, you can go back and forth between the two representations.
Yes.
Okay.
In theory. So what we're going to try and do is somehow come up with a discrete way to on a discrete mesh. So just for simplicity's sake, we'll try and represent that on a curve, and then try and replicate that for a surface. So for a curve, if my normal is in this direction, in this direction at this particular point, and for a different point, the normal is pointing somewhere else and the tangent's pointing somewhere else. What the normal and the tangent directions in these two cases or in this case is not the rotation invariant part, because if I rotate this entire curve, it will be pointing towards different directions, and the tangents would be pointing towards different directions as well. But what's rotation invariant in this is the transform between this frame and this frame. So the transformation that takes me from frame J to frame I is the one that invariant, because even if I rotate and translate this entire curve, this transform will never change unless I change the curve itself. So this transform kind of defines your surface as a change between two adjacent points, and that's why the representation is somewhat differential in the discrete space, and the changes is itself and is kind of independent of wherever the curve lies in the 3 space. And this is true with a surface as well. So for a one ring on a mesh, if I define this frame at the center vertex, and note that in this case I'll have 3 orthonormal axes instead of just 2 in the curve case. I'll have 3 axes defining a frame on top of every single vertex, and I would have such frames on every single vertex on the mesh. What I'm going to encode is how these adjacent frames are related to each other, and that is what is going to form my rotation invariant specification. 3x3 transform, and I'll call it by it's a 3x3 transform which takes one frame in the space of its adjacent frame, and records how much what the transform is that would take that adjacent frame to its neighbor's frame of reference. So this is kind of what we start off our process with, by frames or vertex frames. And the way to find it would be for all vertices, we're going to choose its free, and this is completely arbitrary. All that is just some place to start with. So if this vertex is I and these are J0, J1, J2, and so on up to Jk, then the transform between I and J0 is sorry. So the edge between I and J0 will help us create this vertex frame. Who is do a cross product between the IJ0 edge with its normal, so that I can get this vector, and then cross these two to get this third vector, which gives me a tangent plane on top of every single vertex and a 3-axis orthonormal frame, which is vertex dependent. And I solve and I find this vertex frame the same way for every single vertex. And then what I do is for every single edge that connects to vertices, I would find the transform that takes the vertex frame on V1 to the vertex frame on V0, which becomes my rotation invariant coordinate, or in representation, which encodes the differential changes between two adjacent vertices. So once I have that, I don't have all the information that I need to the mesh. So what I just did is went from this space, which is this mesh, which is defined as XYZ, XYZ, to something that encodes a rotation invariant form between for all edges in the mesh. And this information is not enough to go back to the Cartesian coordinate space, because I still don't know what the should be or what the scale of my mesh is, and how do I connect these. How far should I keep these from each other? So what is important is that now I encode each of the edges length in one of the frames coordinate space. So I'll call these edge coefficients. And all I'm doing here is for each edge, I'm encoding that in this local vertex frame coordinate space. Every single edge becomes some. So frame is defined as AI, BI, and NI. Then each EIJ or be broken down into components of the A axis, the B axis, and so these coefficients, alpha, beta, and gamma, for every single edge is also necessary to go back from this rotation invariant coordinate space to the mesh back again. So these are the two pieces that we pre-compute for the two we have. So one of which becomes the source pose, and the other one becomes the target pose. And for both of these poses, we are computing the vertex frames. And the edge coefficients. And this is all the information that we would need to get the mesh back again. And we can represent all of this information in some form of linear systems so that we can solve for the positions back again. Get there. Also worth mentioning is in this rotation invariant space. I can basically interpolation between these rotation invariant coordinates itself, and what I'll get by going back to my Cartesian space or my Euclidean is the intermediate shape that I'm looking for. So as I was saying before, where we saw the curvature values changing as the mesh was going through some sort of an interpolation. These rotation invariant coordinates are actually representing the curvature changes, and if we blend these curvature changes correctly, then going back to the Euclidean space would get us back the mesh, the intermediate mesh. So so if every ith vertex had fi as its vertex frame, and every jth vertex had fj as its vertex frame, and I and j were in the set of edges, then the rotation invariant coordinate in between them is represented as fi inverse fj, because what I'm trying to find here is what transform would take me from the fj frame to fi frame, and this is the simplest math operation that we'll do in this entire process. A simple way to prove that this is rotation invariant is to actually rotate both of these frames by the same rotation. And if I solve this further, then I get back to the same rotation invariant coordinate. So this is kind of the formal proof where that even with the rotations applied, a global rotation applied to those vertex frames, you're still going to maintain the rotation invariant property of the transform between them. So we're going to use this relationship in our linear system to figure out what the vertex frames would look like for an intermediate shape. So as I said, the rotation invariant coordinates can be linearly blended because they are rotation invariant and are in Euclidean space. So directly blend between these rotation invariant frames, and if I reconstruct these fi and fj for some sort of an intermediate shape to recreate an interpolated shape from target. So the way I'm going to create, so what I'm trying to do is for some blended version of this rotation invariant coordinates, I'm going to try and solve for every fi and every fj, and sum it over the entire mesh or every single one ring. Come up such that the difference between them is exactly the difference between, or the differential change between every single vertex frame is exactly what I specify. So to create this linear system, what I'm going to do is rotation invariant blend in a 3x3 over here, and to multiply it with my ith vertex vertices, and I'm going to then subtract it out of the fj. So what I'm doing is I'm re-inverting the inverse transform that I found and equate that to 0 so that I can minimize their effect. So I can have my fi over here and fj over here. So my rotation invariant coordinates get fi, and then when I subtract it out of my fj, I would get a result of 0 because basically I'm taking the fi frame back to fj as I wanted to. But this rotation invariant coordinate is a blended version of the vertex frames that I found for source and the target. So
now, when you say blended, they're rotation matrices, so you're not linearly interpolating their elements. Are you slurping them, or what does?
Linearly interpolating those 9 values, and it just works.
Wait, that just works? Linearly interpolating rotation values doesn't produce a rotation matrix, does it?
No, it won't. Because when I solve for this fi and fj,
yeah,
because now I have the rotation invariant form of the blended version, and I solve this in a least squares form. And to do that, I would have to constrain at least one vertices rotation invariant frame. So I'm basically saying that one vertex frame has to stay static in its place in the Cartesian, in the Euclidean space, and find me all other frames that that would adhere to whatever the rotation invariant blends tell you to.
No, well, actually, no. I'm more thinking about the rotation invariant matrix itself. So, on the source for an edge, you have a rotation invariant frame that you calculate,
right?
And then the target, which is a deformed, you create a rotation invariant frame,
right,
for the same edge, and they're different.
Yeah.
You're just saying 0.5 times this rotation invariant and 0.5 times that, and add the two?
Yes.
No.
Yeah.
Really? That works?
Yeah.
Oh, wow.
Okay.
And what I would get is our fi and fj, or all the vertex frames, but they're not going to be orthogonal or orthonormal. So to extract the rotation part out of these, I do apply an SVD after the solve.
This is where it gets fixed.
That's where it gets fixed.
And then I do normalize these axes as well, because it's valid for orthonormal frames that I'm going to have to solve another linear system for, so that I can solve for the positions in the Euclidean space. So this was the solve for the vertex frames. So now I have vertex frames, and I do have the blended versions of the edge coefficients as well. So this process, or what I did was I went to linear rotation invariant coordinate space for source and target, found a blend between those blend using those coordinates, and now I'm just taking the mesh back into Euclidean space. So my next solve is going to be for the positions. So once I find these new
That are SVD corrected so that they are pure rotations.
pure rotations,
Okay.
yeah. Although depending on what your application is, just extract an isometric form of that transform as well to allow scale and shear to scale to happen.
Oh, okay.
And now, I wasn't clear about edge coefficients, but edge coefficients are nothing but an ij edge recorded in some vertex frames reference. So if I find this vertex frame and I already have these edge coefficients, which are alpha, beta, and gamma, then I can blend between them as if to say that I'm going to the edge lengths going from source to target, and then find my new edge using these blended coefficients for every single edge. Then I can get back my point positions that I'm looking for. So for that, what I'm going to do is over here I'm going to compute all the edge parameters by multiplying alpha with the vertex frames ith axis, beta with frames jth axis, frames kth axis. Then I find this 3 vector for every single edge, and what is from some point pi to some point pj in the Euclidean space. So if I have my pi over here and pj over here, and I have 1 in my ith place and -1 in my jth place, then I'm saying pi minus pj should be exactly the edge that I encoded using the edge coefficients within a vertex frame. So this matrix is E by P. This is E by 3. So I find these E by 3 by multiplying the edge coefficients with every single vertex frame. And I'm going to state that the difference between these 2 point positions in the Euclidean space should look like this. And again, by constraining 1 point in this system, you can solve it using least squares. And what this would give is the interpolated edge length. So with the rotation invariant transforms or the vertex frames that I found the mesh is going to the mesh is curvature information. With this solve, what I'm doing is I'm interpolating between the edge lengths going from the source to the target, so that I scale the edges properly as well to get the intermediate shape as I go back, as I go towards the target. So yeah, and then you can just blend these rotation invariant coordinates or rotation invariant frames and get the same blends for as many in betweens as you want between source and target. And I can show some examples for that.
Cool. You gotta log in.
So on the left is the linear interpolation, which is doing a linear interpolation between vertex positions, and on the right is the rotation invariant coordinate based interpolation, which is trying to preserve the local curvature as much as possible, and does a pretty good job of interpolating through those vertex frames and through the edge lengths to get all the in-betweens that we want.
What point was the primary point selected for the Luma? It was a reference point, right?
Oh, the ones that are held static in the they're on the right leg. Yeah, it's not here over here. So all of the points that are constrained are linearly interpolated, but everything else on the mesh is using the rotation invariant coordinates. Now this is where we can lose the volume, but the rotation invariant coordinates can preserve it because it's preserving the local surface curvatures as it goes through towards the target pose. And just to give a quick example, I'll quickly set up one.
Old.
No.
Live demo.
So so the one on the left is the linearly interpolated shape. So it's going from this source pose to this target pose. Actually, not this one, sorry.
No, didn't work.
Still.
Put the mouse in there. There you go.
All right. This target pose, and this is an example from the paper. But then what we can do is in practice we'll add the source and the target as the two shapes to interpolate between. And then we have to constrain at least one vertex in the Euclidean space. So we'll grab a few, add that.
You're not typing.
Yeah. There you go.
So so that's how the rotation invariant coordinate solve will look.
How many vertices in this mesh?
I think around
20.
yeah 20.
20,000?
Yeah.
And 2 FPS.
Not bad.
So yeah, the kind of volume preservation is very clearly visible, and that's what the result looks like. And Yeah, it's easy setup, not much effort to do. The only thing that one needs to be careful about is it preserves curvature on a local in a local area. So if you have hands going across each other, which are itself, it can't avoid those kind of self intersections because it doesn't have a collision, a way to solve collisions on,
No, it doesn't
on a
have a
global scale.
global.
There's no collision section in here. You put something through another.
Huh.
Wow. Now, in terms of volume preserving, it is quasi-volume preserving. How much, when does it fail? When does this, have you noticed it?
So the source has a volume and the target has a volume, and those volumes are not necessarily the same, right? You could go from a skinny camel to a fat camel. So it's just volumes.
Yeah, it's just
Preserving in that it's not.
it certainly
not
isn't
constant,
perverting. Yeah, no,
but
it won't
Is it losing more? Is it losing more volume
be. Yeah,
than A or B?
yeah. If those two camels have the same volume, but just different poses, is there at any point on there that there's a max volume? I'm just an intuition kind of thing. Have you noticed?
Not really. The volume is very tightly. Well, the is actually very loosely correlated with itself. So as long as the surface preserves its curvature and the surface area, there's a good chance that you'll end up preserving the volume as well, because your surface area isn't changing a whole lot, at least in the local region. Yeah. So there's no direct relation to any kind of volume preserving property. Some sort of an indirect one from preserving the surface area itself.
You are doing a solve. I wonder if you could put an extra row at the bottom. Interesting. Okay.
I think it's taken care of because OF, edge coefficients, right, which are lengths. So if you had a transformation which was absolutely volume preserved, like volume constant, then for something that's equivalent to a sphere, metric, right? Like nothing can.
Are we sure? All right. Well, anyways, we're getting distracted. This is pretty slick. So what
it is?
What? Well, are we?
Yeah.
Well, we're not done yet. Is there anything more?
This is really nice. And I think you did some experiments that you have your formulation a little bit different than what's in the paper.
Yeah. So the formulation in the linear rotation invariant framework paper is inspired from the moving frames theory of curves. So they also define the transforms that go between adjacent frames in some form of rotation invariant way, using some sort of a representation which is rotation invariant, which is the case with our inverse transform between two adjacent frames is also. But their representation can help you formally prove some of the convergence properties, which again comes from the work that people have done on curves. So, and there are other works which use deformation gradients over triangles as their differential coordinates, which are also rotation invariant when you are calculating them in between two triangles deformation gradients. So that's also a possibility to use as the rotation invariant coordinates. But I guess this description of the rotation invariant transform is the easiest one that I think you can easily compute and handle. And the solvers seem to be a lot stable in this representation as well, because I'm constraining only one vertex and still be able to get a very plausible result out of it. Kind of speaks for the stability that you're getting out of the solve itself.
Cool. I'm still going to go back to that rotation, invariant rotation, and adding them together.
Right.
Wouldn't more rotationally interpolation, like using the spherical linear interpolation, that would produce rotations in between? Have you tried that? And would it affect the solve at all?
I haven't tried it for sure. I have seen papers do is to somehow fit that property in the linear system, which then now doesn't stay a linear solve but becomes non-linear, to try and preserve this orthogonality frames, or sorry, the vertex frames that you're going to find in the first step, to try and preserve some orthogonality in there, make this solution non-linear.
No.
But then you lose out a lot, and seems like the SVD approach is just good enough, which has a parallel to the as rigid as possible as well.
Yeah.
Which kind of also uses SVD quite successfully to try and out the inherently nonlinear nature of interpolating rotations.
Cool. All right. All right. Any other questions? Make sense? All right. Well, thank you, Rishabh. This is awesome. Thank you. So cool. And if you work at Digital Domain and you want to use this, it's called Shapeshifter.
Yeah.
Brilliant. I love that.
And it's released.
Yeah. Yeah. And it's out there. All right. Well, thank you guys. Take a 2-week hiatus as I travel out to Washington, D.C. And we'll be back with probably some machine learning stuff. Yeah.